Thank you for your attendance. As already mentioned, my name is Marcel Dörr. I'm from the Institute for Occupational Safety and Health in St. Augustine, Germany. And today I will talk a bit about the development of high volume hospital sampler with high flow rates. I will start with the aim of the project, followed by some specification standards, especially the 13205 and the EN 481, and then followed by some aerosol chamber and wind tunnel experiments, some measurement uncertainty, and then I will close my presentation with a short summary. So first, the aim. There are already existing 4 different prototypes of personal aerosol sampler for flow rates. They're called UFO1, UFO2, Beetle, and Classic Cone. The UFO2 is a combination of the UFO1 we measured at first and the Beetle. The aim is to choose one of these prototypes to be chosen for further experiments, like in the field and in different workplaces. The second goal is to generate reproducible results, especially for our wind tunnel. It was not quite easy and it was necessary to adjust the measurement setup a bit further. Now the specification of standards. Here we have 5 different, it looks quite normal. The most you can see. So there are five specifications. The first one is their dynamic particle diameter. Because we want to use the sampler to collect inhalable dust, it's necessary to validate them with 9 or more different particle diameter of monodispersed dusts. The next one is the wind velocity. We want to use them for indoor and outdoor workplaces. So it's necessary to measure under 2 different conditions. For indoors, it's 0.1 meter per second, and for outdoor workplaces, it's also 1.0 meter per second. The next one, the wind direction, because these are for personal sampling. It's necessary to validate them while they are rotating continuously or stepwise with 5 or more directions. The next, variability of sampler test samples. The test group needs to be as large as possible with a minimum of 6 sampler. And the last point is the relative standard deviation of dust concentration at the measurement plane. Here's a maximum allowed of 10%. Additionally, according to the, EN 482, it's necessary to have a target concentration about 0.1 to 2.0 of the occupational exposure limit value. For inhalable dust, it's 10 milligram per cubic meter. So now we come to the second standard, the EN 481. Here you can see the sampling efficiency depends on the aerodynamic diameter of the particle. Normally it's decreasing with the increasing particle diameter. The black one is the old or actual version because the standard is under revision. The new version will include 2 curves, the blue one and the orange one. The blue one is for wind velocities about 0.1 meter per second, and the orange one for wind velocities about 1.0 meter per second. Now we come to the experiments. I will start with the aerosol chamber. It was not necessary to adjust the measurement setup, so we can jump directly to the results. I will start with the higher concentration, the 2.0 of the 10 milligram per cubic meter. So standardized is the sampling efficiency of all the sampler according to the FAP. The FAP is our normally used reference. We want to compare the results of different sampler, because FAP is a pseudo-isokinetic sampler. So you can see red lines. Red lines the expected sampling efficiency according to the 481 you saw on the last slide. It was the blue curve. So you can see also that the standard deviation for the fine dusts is quite low compared to the coarse dusts. And the next thing you already saw, I suggest, is that none of these sampler follows the standard, because normally with the coarse dust, the sampling efficiency should be lower than we already measured. And especially for the GSP 3.5, you can see it in orange, it's surprising because we have sufficient information about these sampler that it should follow the standard. So it's quite surprising that this result does not. So I decided to standardize also to the GSP 3.5. And here you can see that more or less all the samples are measured quite the same amount of dust concentration, except with the F400 with a diameter of 34 micrometer. And if you look on the left side, you can see here already that the GSP 3.5 measured the lowest concentration of all the samples. So these were not the only results. We also measured for the low concentration with only 1 milligram per cubic meter. You can see also the red line, and that the standard deviation for the lower concentration is again lower than for the higher concentration. But the main big difference is that you can see here definitely a trend according to the standard 481. It's a big difference compared to the higher concentration. And you can see also with the F400 that the GSP 3.5 measured quite the lowest concentration again. If you standardize to the GSP 3.5 again, this picture looks quite similar to the one with the higher concentration. The sampler measured more or less the same concentration, again, except the F400. So, as I already said, the aim of this project to choose one of these prototypes for further experiment, you can guess it's not quite easy, or to say it's quite impossible with the actual extent of the experiments, because we have to fix two different problems. The first one is why the sampler did not follow the standard for the higher concentration, and the second one is the problems with the F400 for the GSP 3.5 and why it does not follow the standard if it should. So enough with the chamber. Now we come to the wind tunnel. Here was the main focus to get measurement set up to fulfill the specification of standards. So you can see our measurement setup with our measurement plane with the dummy and the two references. The references are necessary, as already said, to compare the results of our prototypes with the one of the references. But with the reference we got a problem with the specification because it's necessary to have maximum standard deviation of 10%. But with references beside the dummy, we enlarged our measuring plane, so a better distribution is necessary to get inside the specification, because we got outside the 10% around 15 or above, depending on the setup. So we decided to put a perforated screen in front of the dummy to cause turbulent airflows and disperse the dust over the whole width of the tunnel to get a better distribution. And it was quite good. We solved our problem with the distribution, but we generated another problem because our second goal was to generate reproducible results. And if you can imagine, if we produce turbulences, it's quite not so easy to get them reproducible. But we can't put something between dummy and the perforated screen to calm the air again, because it would be not so good for our distribution. So normally wind tunnels have in front of the perforated screen a few meters of an approach track to get all the air that gets inside the tunnel as calm as possible, so the turbulences would be more calculatable. But as you can see here, I don't have view meters, I only have a view centimeters. So we decided to put a honeycomb sheet metal to break all the turbulences of the air that comes inside the wind tunnel, and this worked quite well. Because for the first experiments, we use direct displaying sensors, and with this sheet metal in front of the tunnel, we reduced the standard deviation to a third. So it was a quite good calm air in front of the perforated screen and better reproducible experiments on the dummy. So now we come a little bit quite closer to the sampler positioning. Normally the prototypes are on the dummy, but to get a better overview about the distribution, we only use references. So the 3 on the dummy, 3 above, 3 underneath, and 1 on the left and 1 on the right. And now you can see the result of this measurement. You can see that the position 2, 4, 5, 6, and 8 measure quite the same level of concentration. 1, 3, 7, and 9 measured a bit lower, and the 10 and 11 measured the lowest dust concentration of all the references. So if you get more away from the center of the wind tunnel, the lower concentration you will get. So the distribution is not perfect, but overall we got the standard deviation about around 9%. So we fulfilled the specification of 10%, and that was our goal. But we measured only with the fine dust, so the around 10 micrometer. And for inhalable dust, it's the range of 10 micrometer to 100 micrometer. To measure coarse dust, it will be necessary to modify the measurement setup quite further, because with the increasing diameter, the sedimentation effect will increasing too. So distribution to get this distribution will be difficult. So it could be possible to modify the nozzle device for a better distribution, also for coarse dusts. But now we will come to the uncertainty. As already mentioned, we use the FAP for the references, but the FAP has a big disadvantage because we have 30 to 70% of sample adhesion inside the sampler, so-called vent losses. So it was necessary to wash the inside of the sampler and filtrate washing water to don't have so high amounts of mass losses. For the fine dust, we also have mass loss around 2.5%, and for the coarse dusts, we have around 50% mass loss due to this filtration. Our absolute inaccuracy of the scales is 0.01 milligram because the mass of the filter plus the dust isn't quite heavy. The other sample have also sample adhesion, but here we'll talk about 1 to 3%, so it's quite low compared to the FAP and in an acceptable range. Our relative standard deviation in the aerosol chamber is around 4%, and in the wind tunnel, as already mentioned, 9%. The whole measurement uncertainty is still to be defined. So now we'll close my presentation with a short summary. We'll start with the aerosol chamber. 9 dusts are measured, 4 to go. The sample efficiency for the high concentration did not lower with the increasing particle size, and the sampling efficiency for the low concentration follows the N481. So to choose one of the prototype, as already mentioned, are more information necessary, and it's necessary to solve the 2 problems. One, why the high concentration did not follow the standard, and the problems with the GSP 3.5 with the F400. It would be possible to use another charge of the F400 to compare the results with the new charge and the old charge, because there are some information that it could be possible that the charge caused some problems. Now we come to the wind tunnel. Here it was more successfully to determine a measurement setup for the fine dusts, but for the coarse dusts it will be necessary to put it quite further because of the higher sedimentation of the coarse dusts. Modify the nozzle device would be one solution to get a better distribution for all the other dusts. So that was my presentation. Thank you for your attention.